Ahoy students! Today we're going to look at general conics. So we've seen all of the different types of conic sections, and we've seen shifted conics, which aren't centered at the origin. But for the most part, all of the equations that we've seen for conic sections have been in the exact format that we needed to figure out what they look like. But we know that things won't always be put together so nicely. And in fact, if we go and we expand everything out for these equations, we will get something in the form ax squared plus cy squared plus dx plus ey plus f equals 0. Every single conic section that we've seen, if we take the equations with x minus 3 squared and y plus 2 squared, and if we go through and we multiply all of that out and expand it, we're going to get something that looks like this. We'll have an x squared term and or a y squared term. Depends on whether we're looking at a parabola, which only has one of them squared, or an ellipse or a circle or a hyperbola, which has both of them. And if the signs are the same or different, that tells us if we're looking at ellipses or hyperbolas, etc. And we might have linear terms with x and y, as well as a constant term. And so all of the equations that we've seen so far for conic sections, if we expand them out, we'll get something like this. And in general, if we have an equation in this form, most of the time, there are exceptions, and we will see the exceptions, but in general, most of the time, an equation in this form is going to give us a conic section. And to see what type of conic section we're going to get, and to figure out how to graph it, we need to go through the process of completing the square, or the squares, and putting it in the right form. Now this is something that we did when we first looked at circles. We looked at circles whose equations were already in the right form, and then we looked at other equations where we had to complete the square. So we've already kind of done this before for circles, but now we're going to do the same sort of a thing for other shapes. So we're going to look at one example together now, and then I'm going to ask you to click on the linked examples so that you can go through and see some different ones. It's really important to look at several examples so that you can see the different situations that you can run into here. So let's look at our first example. Let's complete the squares and sketch a graph of 9x squared minus 36x plus 4y squared equals 0. All right. Now, we only have to complete the square with the x's because with the y squared term, we've already just got our perfect square. But with the x's, we're going to have to go through and do some work. So, to complete the square for the x's, the first thing we have to do is we actually have to factor out the leading coefficient here so that the x squared is alone. So if we factor out a 9, that leaves us with leftovers x squared minus 4x. And I'm going to leave a little bit of space there to complete the square. And then plus 4y squared equals 0. Now to complete the square here with the x squared minus 4x, we take the coefficient here, negative 4, we divide it by 2 to get negative 2, and then square it to get positive 4. So we need to add 4 there to complete the square. But we need to recognize what we've really added here is 4 times 9, which is 36. So we've added 36 to the left-hand side. To balance this equation, we're going to also have to add 36 to the right-hand side. So on the left-hand side now, we can factor this perfect square trinomial. This gives us 9 times the quantity x minus 2 squared plus 4y squared equals 36. Now, we might recognize this as the equation of an ellipse because we've got x squared and y squared terms, and they're both positive, and they have different coefficients. If they had the same coefficient, it would be a circle, but because they're different, it's an ellipse. And remember, the equation for an ellipse has to have the x and y squared terms adding up to 1. So, to get this in the right form, we need to divide both sides, all of those terms, by 36. When we simplify these, 9/36 reduces to 1/4. So this becomes x minus 2 squared over 4. Plus 4/36 reduces to 1/9. So this becomes y squared over 9. And then 36 divided by 36 is 1. So now we are in the right form for an ellipse, and we can go sketch our graph. We see that x has been replaced by x minus 2. That means that the center is shifted from the origin to the right 2. And y hasn't been replaced with y plus or minus something, it's just y. So we're not going to be shifting vertically, and so the center is just going to be at the point 2, 0. Now, we can see that the larger coefficient is underneath the y squared, so this is going to be an ellipse that is taller than it is wide. Because a squared is 9, that means a is 3, so we're going to go up 3 units and down 3 units to get our vertices. And then b squared is 4. That means we're going to be going to the left and to the right 2 units. B squared is 4, then b is 2. And we have enough points to sketch the graph of the ellipse. And that is our graph. If we were asked for the foci, we could go through and figure those out. If we were asked for other properties, we could do that, but we were just asked to sketch the graph, and so this is what we have. Now, I want to encourage you again to look at some of the other examples, because when we go through, it's going to be a little bit different when we have a parabola. It's going to be a little bit different when we have a hyperbola. You want to get good practice with all these different scenarios. So please go through all of those examples to make sure that you are very well prepared, and then you'll be good.